Welcome everyone. Today I'll be discussing about R-square and standard error in the context of regression. You might be aware that R-square and standard error are widely used statistical terms for quantifying the performance of a machine learning based regression model. So today let us try to understand what R-square and standard error is all about, and we'll try to understand the mathematical equations behind that, and we'll also try to implement the same thing in Python. So to start with, let us look at this particular example. So here we have data for 14 students who participated in a particular exam, and we have the information about the study hours that students spent and also the score that the individual students obtained for the particular exam. Looking at the table itself, you can see that there is a linear relationship underlying. Let us try to make it more clear by plotting it onto a 2D plane or a 2D space. In this space, you can clearly see that there is a linear relationship that exists between study hours and the score. This means that we can build in a linear model that allows us to predict the score based on the study hours. But before going further, let us understand what is variance associated with the dependent variable, which is score in this case. Variance is defined as the average of squared difference between the student score and the mean score that's obtained for all the students. So once you have the variance, you can understand how much the data is distributed away from the mean. Now let us fit a linear model onto this. And let us assume that this is the best fit line that models the relationship between score and study hour. If you provide a study hour as an input to this model, it will provide an estimate for the score, which is as close to the original score as possible for the particular student. So the problem here is that the model here is not completely perfect. You can see that for every student, for example, let's say student S11, the actual value of the score is 8 for that the student studied for about 76 hours. What does the model say? The model says that the student who studied for 76 hours will get a score of about 6.5. So there is a part of this variance in the score that is explained by the model, and there is also a part which is not explained by the model, which is the residual. So in this example S11 here, you can see that there is a part VR, which is the residual part, which is the part which is not explained by the model, and there is a part VE, which is the variance which is explained by the model, and the total variance is the variation, so it's VS. Now we can write that the total variation VS is the sum of VR, which is the residual, plus the V explained. So this is the explained variation this is the unexplained variation, and Vs is the total variation. And now let us try to calculate this for all the points. But you must understand that variation can be positive or negative in this for some of the points. So let us square it and calculate the whole total variation. Let us say the total variation SST equal to SI minus mu of S for all the students. And this is the total variation that is calculated. Let us also calculate the explained variation, which is SI hat, which is the estimated value, minus mu S for all the students. And let's also calculate the unexplained variation. SSR equal to sigma for I equal to n equal to 14 SI minus SI hat. So we can also write that SST equal to SSE plus SSR for the best fit line. Now let us define R square. R-square basically tells us about the proportion of variance in the score that is explained by the model by using this particular input feature variable. So we can write R-square as 1 minus SSR by SST. So this here is the equation for calculating R-square. You can see that SSR by SST tells us the percentage of variance that is unexplained by the model, and 1 minus that gives us the explained variation, which is exactly what R-square tells us. And you can see that the value of R-square always lies between 0 and 1. In this figure, I have shown all the VRs and VEs associated with the particular data points in red and green respectively. So this gives a visual understanding of how much of the variance in score is being captured by the model and how much is the residual associated with it. Now let us define standard error. Standard error is E equal to sigma, which is standard deviation, divided by square root of n. So this gives us the average residual associated with the modeling, the linear model that we have here. So let us try to implement the R-square and standard error in Python, and let us see how it works with evaluating the real life models. So here is a Python implementation where I have used R-square and standard error for quantifying the performance of a linear and nonlinear model fitting obtained using ordinary least square fit. So let us try to go through the code and understand what it is. The first few lines in the code are for importing the necessary libraries, which including pandas, numpy, and matplotlib. And further, I'll be importing the necessary datasets, which includes the linear dataset, which is similar to the one that we used in our example, which is the data which contains student marks and student study hours. And further, we also have a nonlinear dataset, which is in this case is a baseball dataset where we look at the hit distance based on the hit angle. So the first thing that I do here is to plot these two datasets. That's what I do in the subsequent lines. So here, the first part, I am looking at the x values in the linear dataset, the y values in the linear dataset, and then I am plotting them. I'm doing the same thing with the second dataset. And finally, I have two plots, which is as follows. You can see that there is a linear trend in the first dataset, and in the second dataset, it's a non-linear one with probably a quadratic trend. So let us try to also get a summary of the dataset in pandas. So this is how the summary statistics look like for the linear dataset, and this is the summary statistics for the non-linear dataset. Further, I'll define my function for estimating R-square and standard error. So here I am first estimating the mean value of the inputs. I'm calculating the total variance, the explained variance, the residual variance, and here I'm obtaining the standard error. I'm exporting all these values back to the calling function, and I'll be using this multiple times. That's why I define it as a function. So down the line here, I'll be fitting a regression, ordinary least square regression fit on this linear dataset. And before that, I'll be first dividing the input data into training and test sets. The training sets will be used for modeling or estimating the model parameters, and I will evaluate the test set for quantifying the performance of the model. So here I'm using linear regression function to estimate the model parameters, and I'll use predict function here to predict the values for my test set. And further, I will evaluate the accuracy using the function that I defined, R-square, and I'll obtain R-square and other parameters associated with it. I'm doing the same thing with my nonlinear dataset, where I'm trying to model a nonlinear relationship. Here is a quadratic function that I defined, and my objective is to identify the different C0, C1, and C2 parameters. I have to identify those best parameters that best define this model for this particular data set. And further down, you can see the best fitted line for the linear data set and the best fitted curve for the nonlinear data set. You can also see the total variation, the explained variation, and the residual variation associated with the linear fit. You can see that if you add the unexplained variation with the explained variation, in this case, it doesn't add up. You can check it. This is because we have modeled the relationship with our training data, and the model is best fitted for our training data, and we are testing it with the test data, which is a different data set. So in this case, this relationship doesn't stand. So please keep this in mind. The same thing happens with the nonlinear data set. You can get the explained, the unexplained, and the total variation, and you can see similar trends exist. So this is the second step. I'm trying to replace training data by testing data in the prediction step, and I'm using that for the evaluation of R-square. So here I'm using training data instead of the testing data, and let us see how the results look like. So I'm doing the same thing for the nonlinear map, and also we can see that. And now if we add this up, it will add up correctly. Now here we knew that the data set is linear, and directly we try to use a linear data set. So let us see how the linear data set is performing here. You can see that the R2 values is close to 9.96, and it is very high, and also the standard error is very less. So this means that the model is doing good. The similar is case with the nonlinear data set, where we have a prior knowledge of our data set. We knew that it is nonlinear and it looked like a quadratic data set. So we tried to implement a quadratic function onto that, and gave us a good R-square values, and standard error is also very low in this case. But let us try to do something different here. Let us try to see if R-square is really working. So okay, what we can do here is we can try to fit the linear data set with a nonlinear model, and the nonlinear data set with a linear model. Let us try to do that in the upcoming lines. So I'm trying to, the first section is for identifying the nonlinear parameters associated with the nonlinear model, and I'm fitting it on the linear data set. So this whole section is used for that. And in the second section, I'm using the nonlinear data as input. I'm trying to fit a linear model onto that. So this is the same thing repeated, but twisted. So here are the results, what it looked like. So here, the nonlinear model I considered as sine function, and you can see that sine function is not able to capture all the trend in the data, and you can see that the R-square values are very less, and even the standard error values are also very less. And if you look at the nonlinear dataset, where we have tried to fit a linear model onto that, you can see that still the R-square is very bad for that particular model. It means that R-square is able to explain if a model is able to fit the underlying data accurately or not. But you can see that R-square is having a negative value here. Why does this happen? This is because I used the training data for modeling, and for evaluating the R-square values, I've used the test data. So this is a clear example where you can understand that it might not be a good idea to use R-square for quantifying the performance of the model when you are using this model for predicting something. So the takeaway here is that R-square can be used as a good metric for understanding how well you have did the modeling, that is how well you have connected the input to the output. But if you are trying to use this model for prediction, then it might not be a good idea to use just R-square for checking it performance, but you have to look at the standard error, which is more useful in that situations. So thanks for listening, and I hope this video was useful. See you in another video.